we have learned that working stress method lead to your larger cross sectional area, and it was not economical. So for the same reason, there is a high demand to have economical cross sections. And in 1950, ultimate load method was developed, and subsequently it was introduced in India in 1964. To overcome the limitations of work restraint method, in the ultimate load method allow the stress near the your failure. So what happens if you see this graph? In this graph, if we in here you will find that initially we will draw one tangent. So in that tangent, this was linear portion in the working stress method, or you can see this graph. Okay, so basically this graph is idealization of this graph. This graph basically we have idealized, we are neglecting that after the failure, after the maximum load part. So to overcome the limitation of working stress method, ultimate load method allow the stress to reach near your failure. So what we are doing here, if you see this graph is basically idealization of this graph. Here we are basically neglecting that softening part. Okay, so here there will be straight line. So what we are doing here in the work stress method, what we did, we allow the stress up to this much. See, this graph I have considered from the earlier class. So what happens? This graph A corresponding to your actual strength FCK. That graph B is corresponding to the 0.65 FCK, and graph C is corresponding to 0.45 FCK. Okay, if you consider the limit state method. So this graph basically corresponding to limit state method. Now, what happens if you consider working state method? Then allowable state should be somehow below here. Okay, see, it should not be confused because this graph we have considered, because the graph I have considered here is representing ABC graph, that is corresponding to your limit state method region. Limit state, this value basically what happened is coming to be 0.45 FCK. Now see, in the working state method, the allowable stress is low than the 0.45 FCK. The allowable stress is here FCK by 3, so you can say 0.33 FCK. So that value should be somewhere here. Okay. For the time being, we just consider this value. Instead of coming here, we are just representing it here. For the time being, you assume this value is corresponding to our working stress method. Just assume this value here is coming as your linear elastic value. Okay, you just assume this value, though actually it should be somewhere here, but just assume this is here. Okay, so this value corresponding to right now is your 0.33 FCK. Okay, now if you multiply with the some factor of safety, this value will reach somewhere here. Okay, so why I am saying this? Because this graph I already used to define permissible stress for limit state method. So now for limit state method, the value is 0.45 FCK. See graph, so here it should be 0.45 FCK, but for working stress method, okay, that value is 0.33 FCK. So it should be somewhere here. It should be somewhere here. But for the time being, we assume this value. Okay, this value is somewhere here, just in the linear zone. Okay, so this value representing 0.4. This value representing 0.33 FCK, and if you multiply the load factor, it will be your stress under the working load. Okay, since it was based on linear elastic theory, so stress was allowed up to the linear part. Now what ultimate load method is doing? Ultimate load method is allowing the stress to reach your failure. So now if you draw the tangent line, if you extend it, basically ultimate load method is allowing the stress to reach near their ultimate load. Okay, so how it is achieving? It is basically it is applying one load factor. How it is achieving? It is applying one load factor. Whatever the stress is acting on the working load, whatever the stress was developing in the working load, they are applying one load factor. Okay, if you apply the load factor, basically whatever the stress was acting here in that working load, that will be extended to your ultimate load. So To overcome the limitation of working student method, now we are allowing the stress to develop in the structures up to this much. So now what happen if we allow up stress up to this much, that stress also will reach the non-linear stress. So strain will be somewhere here. So if you allow the stress here, okay, now if you extend it, this will be your strain somewhere here. Okay. So what we have learned? We have learned in the working strain method, we are not using any load factor. What we did in the working strain method, you will find that in different combination of load, there is no load factor there. Only there is a combinations, linear combinations, and among the linear combination of different load, we are considering the worst cases or maximum load what was happening occurring worst cases. What are the maximum load is occurring? We are considering that for the working strain method. Now here what we are doing? Here we are introducing one load factor. Okay, first thing we are allowing the stress to reach near your nonlinear zone, near the collapse. Second thing what we are doing? We are introducing one load factor to enhance the load. Basically, we have introduced another term, that is load factor. We have introduced modular ratio in working strain method. In the ultimate load method, we have introduced load factor, and load factor is basically your ultimate load, okay, for which you want to design divided by working load. So how we are achieving the ultimate load? Initially, we are calculating the stress whatever they have occurring in the working load, and then we will multiply with the load factor. If you allow the stress to reach to your failure, since we are allowing the stress to reach near the failure, that cross-sectional dimension also will reduce. So here if you find this example here, this was one column. If the load is constant, if load P is constant, okay, in that case, since we are allowing that for working strain method, since we are allowing lower stress, that cross-sectional area will be high or larger. In case of ultimate load method, since we are allowing the stress to reach near your collapse, cross-section will also reduce. Since cross-section is reduced, it will be economical. This was the main idea about your ultimate load method. Main difference is that we have introduced one term, load factor, for ultimate load method, and we are allowing stress to reach near your nonlinear zone or near your failure. We are providing safety against the collapse. The ultimate load method use different load factor for various kind of load and their combinations. So you will find in the working strain method there is different combinations, but that was only combinations of the load. There is no load factor there. Okay. Here we are introducing one load factor and different load factor for different combination of load, different kind of load and different combination of load. So these are the advantage we have in the ultimate load method. Now what are the disadvantage we have? Since ultimate load method lead to the smaller cross section, okay, in that case there can be excessive deflections or there can be crack also. Okay, so though it is providing safety against the failure or collapse, it will not give a guarantee on the safety against the serviceability, or you can see will not give the guarantee serviceability and the safety criteria together. Ultimate load method also do not consider the effect of creep and the shrinkage. Now another major disadvantage of the ultimate load method is that in the ultimate load method, the stress which is occurring at the ultimate load is basically a stress occurring at the ultimate load is considered as the stress occurring at the service load multiplied by load factor that I just now discussed. Now what is happening here? If you do like this, what happened? Initially you are calculating all the stress in the linear zone, and then based on the linear zone and based on linear elastic theory, and then we are multiplied with some load factor. So whatever the stress we will calculate, that also will come as a linear elastic zone. So whatever the calculations we will do, that also will be based on linear elastic theory. But at the same time, stress also reach to the non-linear zone. So you can see there is some flaws. First we are calculating the stress under working load, and then we are multiplied it to have the stress under ultimate load. So these things is based on your linear elastic theory in the ultimate load case. At the same time, when you applied ultimate load or load near the failure, concrete already reaches to the non-linear zone, or structure already reaches to non-linear zone or inelastic zone. Okay, so you will see there is some conceptual mismatch. First is based on linear elastic theory in the ultimate load case. At the same time, structure also lead to the non-linear zone. Here you can see this example. Initially we calculate all the stress here and then multiplied here, so it will reach here somewhere here, and according to that we'll do all the calculation. We'll calculate the stress, we'll calculate strain. So whatever the theoretical calculation we will do, okay, strain will be somewhere here based on your linear elastic theory at the ultimate load using ultimate load method. Then in actual case, what happened at this stage, concrete will lead to the strain of up to this much. If you draw one line here, the strain will be somewhere here. Okay, so you will find there is a large deviation between your predicted result in the ultimate load method and what is happening in the actual concrete or in the actual concrete structure. If you want to apply this method for your case, what have to do? You have to have a realistic model of stress strain for your concrete, for a particular concrete what you want to use in your design purpose, because it is heterogeneous in nature and it will be very difficult for you to have unique stress strain result. In case of linear analysis, we have done that if you know that strain conditions and if you multiply the Young modulus, you can predict the stress. But if we considering the nonlinear zone, in that case directly you cannot have stress is equal to E into epsilon, okay, Young modulus into the strain. Here you will find that stress also is function of modulus as well as the strain. There you have to draw one tangent at each point and you have to see how the tangent is behaving. Depending on that, you have to predict the stress. And since concrete is heterogeneous in nature and there are a lot of factors which is influencing the stress strain behavior, it will be very difficult for you to have a unique stress strain curve. Okay, so if you want to use ultimate load method, in that case you should have a proper knowledge, okay, of the nonlinear behavior of the concrete. To have, if you want to use ultimate load method in proper way, in that case you should have proper knowledge of stress strain behavior in the inelastic zone of the concrete, then only you can use it. Okay, otherwise it is not recommended, is not advisable to use ultimate load method for your design purpose.